xz and gamma yz. Yes?
Will gamma always be between 0 and 90?
That one we will have the series definition when in the later chapters. But the definition, the sign convention for shearing is very ambiguous. Okay, it's very ambiguous, but that's a very good question. So I think later on into chapter 6, that is a total different topic. We talk about the transformation of the stress. To that point, I will seriously give you the sign convention. But at this moment, if for all of your exercise, if you can give the quantity, and then, for example, in the test or in any communication, you give the quantity, and on your paper, you simply describe which direction, on which side that rotate, and that'll be good.
Okay.
Okay. So now we have the shear strength, and then here we have defined Hooke's law. So right now I'm going to I fix this one. I'm going to introduce what is G. I'm going to complete Hooke's law. So right now we have learned is only half of the 6 equations. So for the normal part, that is epsilon x equal to z sigma x minus mu e sigma y plus sigma z, and this is sigma y minus mu e sigma x plus sigma z, and sigma z e minus mu sigma x plus sigma y. So this is only half of them, and right now we have learned the shearing. So for the shearing part, we have at least gamma xy, gamma xz, and gamma yz. And that will be corresponding is the shear stress induced. So if you like, maybe I can specify this. It should be gamma xy, for example. Okay. So for this case, this will be equal to the magnitude of the shear stress divided by G. That's it. So what is G? Basically, G is equal to, for simplicity, tau equal to G times gamma. For general shear stress, equal to G times the corresponding shear strength. Okay, so let me finish this one. So that would be tau xz divided by G. This is tau yz divided by G. 1, 2, 3, 4, 5, 6 equations form the complete generalized Hooke's law. Furthermore, if we want to consider thermal loadings, then the thermal coefficients alpha. So here we have alpha times delta T. Delta T is a thermal loading. Alpha times delta T. And for most of the isotropic, which means one material, alpha should be constant in all the directions. And again, in the shearing, we define this. All the shearing stress is that won't change the volume. So that means for all the temperature with the thermal loading, it will only affect the volume change. So that means the temperature influence of temperature loading won't doesn't come to the shearing part. Okay, the thermal loading is the influence of the volume change. So that means only appear to the normal portions here. So this is the 1, 2, 3, 4, 5, 6. That is a complete description of Hooke's law. So right now we pretty much complete the information, and this is a very straightforward examples here. For this case, this is a sandwich-like structure, and only the middle one is elastic, and top and the bottom is solid. Solid, that means won't deform. And for this case, we apply the loading on the top. So this loading basically is through the solid plate and uniformly applied to the middle material. So that means this P will induce shearing force and equivalently shearing stress on the top surface to drag the change of the material. So that material basically, the problem statement can be described by this. So our material model is this, and the bottom is fixed. And on the top, we have the shear stress, and equal to P divided by the area on the top surface, and here the area equal to 2.5 by 8. Okay, so from here you can see that this is going to make a change of the shape. So for example, that's going to become like this. And again, here I exaggerate the change of the shape, but in reality, this angle should be very small. Okay, and this is our gamma shear strength. Yes.
For H, that is 2.5 times 8 meters squared?
Inch square.
Inch square.
Inch
Okay.
square, yes. That is inch. Okay, so now for these questions, we are given the G. G is given equal to 90 KSI. And the top plate moves by 0.04 inch. So that means this distance here we measure is 0.04 inch. So therefore, if we utilize this triangle here, so this is 0.04, and the length, the height is 2 inch here. So gamma, basically using this triangle, we can see tangent gamma equal to 0.4 divided by 2. Because in my mind, I always learn my trigonometry is in this orientation. So sometimes I need to tweak my head into this orientation. Okay, but anyhow. Okay, so in this way, the gamma is equal to arctangent 0.02. And this is a very small number, so basically we can approximate just equal to 0.02. That should be fine. Or otherwise, you can punch your calculator, but that number should be very close. So the average shear strength, the first question, this is shear strength equal to 0.02. Again, what is shear strength? That is a change of the size, and that is the angle. The second question, the force P, we need to determine what is the magnitude of the force P to cause such a change. So in this case, let me erase this one here. So therefore, P by tau equal to P over A. On the other side, using Hooke's law, tau equal to G times gamma. So here the G equal to 90 times 3 PSI. PSI is the pounds per inch square. And times gamma, we calculated is 0.02. So equal to tau equal to P over A. So here we can calculate P should be equal to this number multiplied with A. 90 times to the 3 times 0.02 and multiply with area, and area this one equal to 20 inch square. Okay, so we pay attention on the unit here. This should be equal to pounds. Okay, this one should be equal to pounds.
I'm having some trouble following. So you're going from the equals pressure divided by area, and then what are those numbers that you're plugging in?
Yes. Let me do this again one more time. Right in the good way. Tau on one side equal to P over A. Okay, parking from here. And the other side, this equal using our Hooke's law, G times gamma.
Yeah.
So therefore, P will be equal to G times gamma times A. So plug in the numbers, G equal to 90 KSI times to the 3 is this one. And gamma, we simply calculated already 0.02. And area is equal to 20 inch squared. So basically here we cancel the inch square here. So we can obtain the value equal to how much? 90.
Are you measuring gamma in radians or degrees?
Gamma is radian.
Radians.
Radian. Okay, that should be this number. Are we right? Okay. So that is for your reference.
That was a side profile view, that's not from the end. That your picture is drawn there is like a side view. Do you measure on the length? It says 8 on that is the ball.
Yeah, this is a side view, right? And that's for 3D, assuming for the 3D, we're assuming the whole thing just move uniformly.
So like where would the 8 inches and the 2.5 inches be on your diagram there?
We look at the problem statement one more time. You can see this plate, the force is applied to the top, right? So this force is parallel to this surface. So that means shear stress will be induced on the top here. The shear stress will apply to this top. Are we okay? And now which I draw is this view. This view. Okay, so next page will be so right now you can see when you drag it, and actually what I draw is this viewpoint. Okay.
Gotcha, because you just drew a square. And
I just square. Yes, I'm sorry. If maybe I can drag it a little lower.
Gotcha.
Okay. Look at here. In the textbook, a drawing is a curve, and if the force applied is too big, is a little bit bigger, then actually the change of the side, that should be a curve. It shouldn't be the straight line. But here for illustrations, here that should be the. We just simply simplify that one as a straight line. Yeah, just for your. This quantity, and again, how many material properties we have? We have 5 material properties. We give the Young's modulus E Poisson ratio and the thermal coefficients. So for this one, as long as we give, for example, the 2 quantities, then we have derived the Bach modulus, that is E 3 times 1 plus 2 nu. And also from the 2 quantities, we can derive in a certain way is E 2 1 plus, I forgot this number, 2 nu, right? 1 plus nu, sorry. So here just tell you, as long as we know 2, then we can have the other 2. Okay. And this is the specific, that is right for the elasticity, and the textbook give us a very detailed justification for this relation, but that is not that important, so let me skip over those things. And here in ES 331, I don't want to consider the composite material. Composite material is like this. I will be offering the intermediate mechanics material in the following in the spring semester, just next semester. That one I will talk about. I will try to cover all these sections here. We're going to skip. If you turn over the textbook, the table of the contents, there's quite a few sections initiated with the asterisk, the stop mark. Those sections are a little bit more advanced, and I don't want to cover it because due to the time constraint. But those sections will be covered in the intermediate mechanics materials. For example, the composite material could be will be the one topic, not we described here, but next semesters. Here sometimes you heard from me. I use this one called the isotropic material. Here, just the kind of the talking. These terms didn't show up in our textbook. But anyhow, isotropic material is that the material properties are the same in all the directions. Which means, for example, if you throw a pipe, a cake, to the face of your friend, if that cake is made of the isotropic, then it really doesn't matter which side, front side you throw in, the cake will deform in the same way. If that cake is not isotropic, then the deformation from each side will be different. And specific to that one, we call the anisotropic. And furthermore, we have the clarified is orthotropic. Orthotropic material, that means the material properties will depend on X, Y, Z direction. The three directions are normal to each other. Or otherwise, for the most general, it's just anisotropic. That is direction dependent, but the direction doesn't have to be normal to each other. So those properties, I will have discussions, not here, okay? So for all the composite material like this, for example, for civil engineering, you make a concrete. Before you make a concrete, you put the steel bars, and to enhance the structure, those one will be the one good example of the composite, or fibers. Your clothes and our clothes is the composite, basically the fiber put into the different ways, or composite woods or laminated woods. That is one example here. Those things will involve the the direction dependent justification, and that one will make things a bit more complicated. So we skip all those things. So on my slides, as long as I put a symbol skip, then that is a topic I won't cover in this semester. Okay, now we change to the different topic. That is the last topic in chapter 2. And actually chapter 2 is a huge chapter. But because here we kind of lay down a lot of the fundamental concepts. This is the last one. And basically this one I'm going to introduce, we're going to use a curve to approximate the values of the stress concentration. This could be the only place, and